So a transformer is always going to have two windings in it. We're always going to have a primary winding. So we'll always have a primary winding, and then we're always going to have a secondary winding. And what those two windings give us the ability to do is to energize one of them. So depending on which one we want to use, and here's our windings in here. This is one, and this is the second one. You can see them through the clear plastic tape. This is just kind of a mounting bracket, and so we have the primary, the secondary, and then of course we have the core of the transformer. And this one happens to be a laminated core. You can kind of see that if I hold it close enough. You'll see it's laminated pieces of metal, and then typically they run a weld along one edge to kind of hold that all together. So that forms the core of the transformer. And what we're doing with this transformer is when we say we energize the primary, and this transformer has some versatility in that it's a multi-tap transformer. You can see we've got a couple of voltage options here on the primary. We've got this terminal over here. This is called the common terminal, and it's in common with either this terminal or this terminal right here. So if we're going to use 240 volt for the primary, we would use this terminal and that terminal. And if we were using 208 volt for the primary, we'd use that terminal and that terminal. And our only two options are down here on the secondary side are for 24 volts. So on the secondary, we're looking for 24 volts. And the primary, we have the two options of either 208 and 240. So when the guy makes a transformer, it's obviously easier to make kind of a two-size or a one-size-fits-all application. So we've got one transformer here, can do a couple of different things, but the output voltage obviously is 24 volts, so that's going to be consistent in this case. So again, I'm going to kind of give you a little indication of how this transformer works. I've got my meter again. I'm going to set my meter to continuity. So we're testing for a complete path again. So anytime I have a transformer, I should always have a good secondary winding, and I should have a good primary winding. So I've got a complete path on the primary, got a complete path on both primary windings, or what I'm doing is this is simply manipulating the coil, and it's the same coil, it's just grabbing it at a different point. So this part here might be a little bit longer than, say, this point right here. But pay attention, when I go from this terminal here to over here, notice what happens. I don't have any continuity. There's no complete path from the common to either of these terminals or to either of those terminals. If I do, then I have some kind of an issue, because remember, the transformer is two separate coils of wire. So what we're doing is we're making a magnetic field with one of those coils, and then that magnetic field is going to bleed over into the other coil, and that's going to make that secondary voltage that we're going to be able to take advantage of. The transformer can function both ways. We could put 24 volts in as our primary, and then we could get 240 or 208. Or what this one's designed for is it's going to transform down, it's going to step down, so it's going to take a high voltage and going to make that magnetic field, and we're going to create a lower voltage source. One other thing to note is the resistance of these windings should always have some resistance. So if I measure the 208 volt portion of the primary winding, I'm looking at 32.3 ohms. And the 240, so I'm changing the length of that primary winding just a bit. I'm at 36.7. Resistance changed. And let's see what I'm at here on my secondary winding. I have just a really small value of 0.6 ohms. Now if we turn this over one more time, and if you look really carefully, it might be difficult to see, but you'll see that this winding here is the secondary winding, and it is made of thicker wire. The primary winding is up here. It is made of thinner wire, so obviously thicker wire, less resistance. This is our secondary winding. So the last use for an electromagnetic field or electromagnet is this item right here, and this is a small induction motor. And this is another really great example of a coil. You can see the coil of wire very easily here. It's wrapped around this plastic piece kind of as a containment unit, but then notice what's it really wrapped around? It's really wrapped around this steel core, and again this one is laminated also. If you can look, you can see the tiny laminations there. I think if I hold it just right. And again, it's usually kind of welded or stuck together someplace. A couple of rivets here that hold it together. And inside of here then is the rotor of the motor, and it is made up of segmented pieces of steel. And what happens once this coil here is energized, in this case with 120 volts, you can see on this side right here, it's a 120 volt motor. So you put power to the coil, it induces a magnetic field into this rotor, and that rotor is attracted by that magnetic field, and the rotor spins. Now, does this process work in reverse? Yes, it does. Keep in mind, anytime we're going to generate electricity, we're going to use some type of a generator, which is going to be some permanent magnets mounted on some type of a device that spins, and we are going to spin that device through an external source, maybe a gasoline engine, diesel engine, a steam turbine, something like that. And what happens then is those permanent magnets rotate in a coil, and you induce a voltage into the coil, and you get AC voltage. And if you look carefully at my meter when I spin this, you can see that I can induce some voltage into this coil here by just simply turning this rotor. Obviously I'm not spinning it as fast as it needs to make 120, but you get the idea. So how does that motor generate that magnetic field? Well, number one, the coil of the motor, or in the case of a single-phase motor or even a three-phase motor, it might have multiple coils or multiple windings. A lot of times coils are referred to as windings in the motor. Those windings are all going to have some resistance. So notice that this coil here has some resistance, 27.3 ohms of resistance. And as long as we put a voltage source on there, that resistance creates some current. And we remember from the definition of electromagnetic, as soon as we have current flowing down a wire, we have a magnetic field, and that magnetic field then is what turns the rotor of the motor. So our motor is always going to have resistance, and it's also always going to have continuity on that winding. So again, if you are doing some troubleshooting and you're having some trouble, your motor isn't functioning properly, one of the first tests to do is just check to see if there's continuity. If you have continuity on all of your windings, then you can begin to compare those windings to one another and do some resistance checking, and the resistances should all match as well.